All right, so we are finishing up our last week in chapter 4, which means next week you're going to have your chapter 4 test. It'll work just like usual. You'll have the test starting on Thursday and Friday to work on, and you'll have the week in advance to prepare. And you just want to meet with me sometime between now and that test to go over any questions, talk about any larger concerns that you or I might have about the exam, and for me to check your homework notebook and notes. So speaking of notes, let's get ourselves ready, and we're going to get started on our last topic of chapter 4, which is antiderivatives. So you'll notice here you've got 2 days that you're working on, so 2 problem sets with 2 different homework assignments that I want to see turned in. So we're going to do one longer video, and then you'll have a good amount of work time on the second day to just work through problems and get that practice in. So the first thing I want to do is define what an antiderivative is. Now, an antiderivative is kind of what it sounds like. It's the way that we'd write it mathematically is we'd say that the antiderivative is, usually we use capital letters for these, so it's f of x, where the derivative of big F of x is equal to the function that you have. So the question is really, what equation has that derivative? So if I'm just going to jump immediately to looking at an example, like number 1, a dy dx is equal to 2x. And so this is asking, what function has the derivative equal to 2x. So this is basically just looking at your formulas and working backwards. So you can look through your notes, you can look through the problems we've done before, and you can say, oh, well, then y is equal to x squared, because the derivative of x squared is 2x. So a lot of these are going to go back to those formulas that we did in chapter 3, and just asking yourself this basic question. What function has the derivative of 2x? So we're finding the antiderivative. Here it says f prime of t is equal to e to the t. You again ask, what has the derivative equal to e to the t? Now you think about it and you're like, oh, well then f of t is equal to e to the t as well, because e to the t has the derivative is itself. Now, of course, these are going to become more challenging. So here, for example, we have f of theta is equal to sine of theta. And as you may recall, you're like, okay, well, I know something has the derivative of almost sine of theta. If you recall, d theta of cosine is equal to negative sine of theta. So it's like, okay, well, this is almost what I see here, but there's this negative that isn't in the original function. And so what you want to think about this as is a coefficient rule, because you can say, well, this is negative 1 times negative sine theta. So then the antiderivative, f of theta, is equal to negative 1 times cosine. Because these two, that's the antiderivative, but then you need to account for the negative, so you're like, oh, it had a coefficient. Same thing would be true if this had, a negative 7 in front of it. You'd say, oh, well, the coefficient is 7, because those just stay in the front. So f, the antiderivative of theta, in this case, is negative cosine of theta. So those are your common ones where it's like, oh, it looks just like what it is. Now, of course, you're going to have more complicated examples. So, for example, in D, it says f double prime, so you might have the second derivative. That's absolutely fine. When we take the antiderivative of a second derivative, it gives us the first derivative of 2 plus 12x to the third minus x to the fifth. And this is a really helpful idea because then you have the antiderivative power rule. So whenever you have a polynomial, just like with the derivative power rule, it was you bring the exponent down and subtract 1. So if you recall, the derivative of x to the n is n to the x times x to the n minus 1. That means that if the derivative of a function is equal to x to the n, then the antiderivative, so f by itself, then f of x is equal to 1 over n plus 1 x to the n plus 1. So the important part here is that when you differentiated, you subtracted 1. When you antidifferentiate, you add 1 to the power. Hopefully that makes sense. And then your coefficient is 1 over n plus 1. And the idea with this is that if I took the derivative of here, this power comes down, and then these two would cancel out. So if you have no coefficient here, it's because the power came down, canceled with the denominator. So we can use those for these terms. Also, one that's just really helpful to remember is that if you have the antiderivative of just a regular term like this, a constant, this would become, 2x. Right? If it doesn't have any power, that means that it had the derivative of 2x is 2. So we'll start there. F prime, because that's the antiderivative of f double prime, is 2x. You carry each one separately. So then this would be 12 for the coefficient, which you can also think about separately. And then I'm just going to use the anti-power rule and say, well, this is going to be x to the 3 plus 1, which is 4, minus 1 over 5 plus 1, which is 6, x to the 5 plus 1. Simplified, that's 2x plus 3, since I can simplify the coefficients in front, x to the 4 minus 1/6 x to the 6th for my antiderivative. So for some of these, it's just going to be, oh, I recognize them from our previous formulas. Maybe there's a coefficient involved, and for some, you're going to want to use the anti-power rule. Now, what you'll notice here is that these are the general antiderivatives. Now, the problem with a derivative is that if I have the derivative of a constant, so the idea here is, recall that if I take the derivative of just some constant c, that's equal to 0. So all of these might have like an imaginary 0 here, and then I'd have a plus c for some constant, but I don't know that because in a simplified version I haven't written it. And so when this plus c disappears, that means that we might need to find it. And so what you're given often is that if you are given a specific here, this means that you can find that plus c. And so we're going to walk through that process. So here it says find f given f prime is equal 2 to the x minus root x over x. So in this case, the first thing I'm going to do, just like I would for derivatives, is simplify it into powers. So I'm going to say that, all right, well then f prime of x is equal to 2x over x minus x to the 1/2 over x, which I can simplify as f prime is equal to 2 minus x to the negative 1/2. Now I'm going to use, since these are both polynomial terms, I'm just going to use the anti-power rule. And I'm going to say then f prime, f tells us that f of x by itself is equal to 2x for the 2 minus 1 over negative 1/2 plus 1, which is positive, and you can do the same thing to the power. So plus 1. And then we are going to say, all right, well, we're going to find that plus c. So I'm going to put that on there. And I'm going to simplify before I solve for it. I'm going to say this is 2x minus 1 over negative a half plus 1 is 1 over 1/2, which is 2. And this becomes x to the 1/2, so this is just root x plus c. So what I'm going to do next then is, now that I have a simplified antiderivative, I know that f of 4 is equal to 1. So if I know that f of 4 is equal to 1, that means that I can replace f of x with 1 if I replace x with 4. And then all I want to do is solve for c. So 1 is equal to 8 minus 2 times root 4, which is 2 times 2. So then I've got 1 equals 8 minus 4 plus c. So that means 1 is equal to 4 plus c, meaning that negative 3 is equal to c. So my final answer is f of x is equal to 2x minus 2 root x minus 3 for the c value. And this would be the specific antiderivative given that condition that f of 4 is equal to 1. All right, let me know if you have questions about antiderivatives or about anything in Chapter 4 in general. Be sure to nominate any problems you're stuck on in the forums, and please do reach out by email, by comments, or set up a Zoom meeting, and I'll talk to you later.